fMRI is the modern neuroimaging technique most associated with neuroscience. It's the one everybody knows about. It's the one that you see the pretty pictures of with all the bright colours in the newspapers. It's a technique for seeing inside a living skull. So whereas before we always used to have to cut things open, do fairly invasive surgery on very delicate brain tissue, now you don't have to do that. You can just put someone in a scanner and you can look at what their brain is doing in real time as it gets on with its everyday stuff, whether that be taking a decision or looking at an image or listening to a sound or whatever. So fMRI is a very useful technique. It's one of 3 neuroimaging techniques that I'm going to talk about, and it's by far the best known. And it's been around for, say, 20-30 years, but it's only really taken off in the last 10 or 15. It stands for functional magnetic resonance imaging. I'm going to say a bit more about what that means. There are actually 2 kinds of MRI, functional and structural, and both are used in the kind of fMRI scan that you would get when you go into hospital, for example. Okay, so when you go for an MRI scan in hospital, there are 2 kinds of MRI that are actually going to be done during that scan. The first is structural MRI, which is basically looking at, as the name suggests, at the structures of the brain. It gives you a picture of, if you like, the architecture, where the thalamus is, where the ventricles are, the grey matter, the white matter. On top of that, you then put the functional fMRI, and that is looking at activity, what the brain's actually doing. So one is, if you like, getting the overall picture, and then onto that picture you're mapping activity, brain function. So how does fMRI work? Well, MRI in general, magnetic resonance imaging, uses the physical principle of resonance, and it also uses a magnetic field applied across the brain. Why is that necessary? Well, you're trying to measure blood flow effectively for functional and water content for structural. I'll unpack that a bit. The brain is full of water. Now, water is H2O, H being hydrogen, O being oxygen, and that H2O tends to dissociate into an OH, what they call a radical, a hydroxyl radical, and an H+, which is a hydrogen ion. Now, a hydrogen ion is nothing more than a proton. It's a single proton, and it has a magnetic moment. What that means is that it's susceptible to magnetic influence, so if you put a magnetic field across it, it will tilt to align. So if you think of it as a tiny bar magnet, the hydrogen ion, the proton, will tilt to line up along the magnetic field. And what that means is that you can influence the direction in which those things line up by changing the magnetic field across the brain. So the first thing you need for MRI is a magnetic field. The second thing you need to understand is that blood, which is what is being measured in fMRI, has different magnetic signatures, if you like. It behaves differently depending on whether it's coming into the brain and carrying oxygen, or whether it's going out of the brain, deoxygenated blood, going back to the lungs for a refill. So whereas for structural fMRI, you're just looking at the water content and you're relying on the fact that different types of brain tissue have different amounts of water. So fat has a different amount of water content from, say, the ventricles, which are full of cerebrospinal fluid, which in turn has a different content from neurons. That's how you build up a structural MRI, but for functional MRI you're looking at blood flow. And so what you have is a difference between blood coming in, oxygenated blood, and blood going out, deoxygenated blood. And you can detect that by the change in the magnetic field, because as the blood loses its oxygen, the magnetic signature shifts. So you can pick that up. And the third thing you need is where the resonance comes in. Now, these protons are able to absorb. This is getting a bit more into subatomic physics than I want to go, but basically protons are able to absorb radio waves at a certain frequency. And what happens is that they can absorb the radio waves, which is just a packet of energy, and store it for a little time and then release it. So what happens in fMRI is that a pulse of radio energy is put into the brain. The protons absorb that energy and then they can release it, and that energy is the same, so it's another radio pulse. So basically what you're doing is you're making these protons emit radio pulses, and it's those that the scanner will actually detect. So a magnetic field by itself isn't enough to do it. You need to have something to actually detect, and so you do that by using these radio pulses. So what you've got is a combination, a magnetic field applied across the brain, the changing magnetic properties of blood as it delivers its oxygen fuel, and these radio waves which are used to make a detectable signal. And that's how fMRI works.